Alright, so we're going to start with section 4.51, which is the steady state forms of the mass and energy balance. So we've seen this equation right here in many different forms, right, so far. We've seen, this right here specifically, but we're going to reduce that a little bit, right? And I know we did this the last time where we reduced it because we found out that it was a steady state balance through the question that we did. And so that right there is the key word, is steady state. So let's go ahead and start. We've seen this first equation right here is the summation of mass inlet has to be equal to the mass of the exits. This is just the conservation of mass principle. And then it says at steady state, the energy of the control volume with respect to time does not change, right? So it can be rewritten as the following. It can go where that goes to 0 and it's QCV, so Q of the control volume and work of the control volume has to be, or is added, all this equals 0, to the summation of the energy of the inlet and the summation of the energy of the outlet. And when I say energy, I mean all types. I mean work of the fluid, velocity, which is kinetic energy, and potential, right? So the energy forms that we care about. And then they just rewrote this, right? Essentially, they just moved it to different sides and got these two together. So it says, equation 4.6 asserts that steady state, the total rate at which mass enters the control volume equals the total rate at which mass exits. Similarly, equation 4.19 asserts that the total rate at which energy is transferred in equals the total rate at which energy is transferred out. Many important applications involve one inlet, one exit control volumes at steady state. It is instructive to apply the mass and energy rate balances to this special case. The mass rate balance reduces simply to M1 is equal to M2. So I did this last class, right, where I said M1 is equal to M2. Essentially what this means is that the mass flow rate entering equals the mass flow rate exiting. And instead of using I's and E's, we use 1 and 2 because that denotes state points, right? From before the process and then after the process is 1 to 2. It says, that is, the mass flow rate must be the same at the exit state 2 as the inlet state 1. The common mass flow rate is designated simply by m dot. Next, applying the energy rate balance and factoring the mass flow rate gives this. So we have seen this equation in our example yesterday. This right here, it was the same equation as before, except that we don't have to sum the mass flow rate entering and exiting because we know that the mass flow rate is the same. And therefore, if we know that they're the same, you can factor that out, and what is left is essentially this. It's H1 minus H2, these two minus each other, the velocities, and then the potential energies subtracted off each other. So you end up with this, which we saw last time. I think we've got a decent grip on how that works. And then what they did was, in the next equation, they divided by mass. So if your question does not ask for it in, like, let's say it doesn't ask for your answer in terms of like kilowatts or a total energy, dividing by mass, you get, this would be in kilojoules per kilogram, everything would then have to be in kilojoules per kilogram, or BTUs per pound. So they just did work per mass or heat per mass, right? Alright. Let's see if there's anything else we need to talk about here. No. Alright. So it says modeling considerations for control volumes at steady state. In this section, we provide the basis for subsequent applications by considering the models of control volumes at steady state. In particular, several applications are given in sections 4.6 and 4.11. So those are the applications that I've talked about. That's like the nozzles, the diffusers, compressor, turbine, and then valves and heat exchangers would be the last ones. These are the major things you will see in this class ever. I think pump is the only other thing you will ever see. Are those like 6 or 7 processes. So it says, showing the use of principles of conservation of mass and energy together with relationships among properties for the analysis of control volumes at steady state. The examples are drawn from applications of general interest to engineers and are chosen to illustrate the points common to all such analysis. Before studying them, it is recommended that you review the methodology for problem solving outlined in 1.9. As problems become more complicated, the use of a systematic problem solving approach becomes increasingly important. And so what they mean is essentially how we've been doing things is that, you read the question, you write what you know, you figure out what links the state 1 to state 2, you follow that link to get everything about state 2, and then you eventually, get all of your H's and V's and all that, and you solve for the answers that they ask for. And you write, I think the most important thing is that whenever you get one of these questions, like say it's a valve or a turbine or whatever it is, you write the equation for a turbine immediately down on the paper. And the reason is because then you can start from there and go, I have this, I have this, I don't have this, I don't have this, I have to find those two things. And it helps you guide yourself to the right place. So, it says, when the mass and energy rate balances are applied to a control volume, simplifications are normally needed to make the analysis manageable. That is, the control volume of interest is modeled by making assumptions. So those assumptions that we make are basically making the question doable, right? Because if we didn't, for example, if the question didn't say anything about heat transfer applications, like is this thing losing heat to the outside, if it never said anything about work, we could never tell. We couldn't solve this question in good faith because we didn't know those things. So we have to make assumptions that reduce the equation down to something more manageable with the information that we have. So it says the careful and conscious step of listing assumptions is necessary in every engineering analysis. Therefore, an important part of this section is devoted to considering various assumptions that are commonly made when applying the conservation principles to different types of devices. As you study examples presented in the next sections, it is important to recognize the role played by careful assumption making in arriving at solutions. In each case considered, steady state operation is assumed. The flow is regarded as one-dimensional at places where mass enters the control volume and exits. Also, at each of these locations, equilibrium property relations are assumed to apply. So these are some of our assumptions that we're making. So, it says, in several of the examples to follow, the heat transfer term QCV is set to 0 in the energy rate balance because it is small relative to other energy transfers across the boundary. This may result in one of the more following factors. So what it means by this right here, the heat transfer term is set to 0 because it is small relative to other things. So let's say our kilojoules per kilogram are in the thousands, right? Our velocities are in the thousands. Basically everything is really high, and the heat transfer at the end, and the heat transfer leaving is 1 kilowatt, or one watt or something. That is negligible when compared to the amount of numbers that we're getting, right? Like, so essentially think of it this way, is like, what is if I said that I have $1 million and a penny was added to it, would you guys say that I have very much more money? Like, would I have anything different, really? Not really, right? So essentially what it's saying is that comparative to the larger scale, one thing might be really small. And so we tend to get rid of those things. And you will see this in a couple other examples as well. There are some times where you get rid of inlet velocity, sometimes where you get rid of a couple other things. So we'll work on that in just a second. But I just want to make sure you guys are aware of where this comes from. So it says changing it to 0 relative to other energy transfers could be the result, and this may be the result of one of the following more factors. So the outer surface of the control volume is well insulated. That would require heat transfer to just basically assume 0. The outer surface area is too small for there to be effective heat transfer. The temperature difference between the control volume and its surroundings is so small that the heat transfer can be ignored. So essentially, if the outer temperature is 70 degrees and our control volume is 71, the heat transfer there is not very high, right? Because their temperature differences are very small. So it could be 0. And it says the gas or liquid passes through the control volume so quickly that there is not enough time for significant heat transfer to occur. So this is like kind of in your mind, is that if you have like a 20-foot long pipe, right? And the pipe is being heated to a really high degree. If you shoot the fluid there too fast, it won't heat up because it didn't have enough time to really absorb any of the heat that's being put into it. So that's some of the effects that could happen. This could be it says this may be the result of one or more following factors. So essentially, this is kind of like real world applications of why you might neglect these. All right. And then it says the work term, work CV, drops out of the energy rate balance when there are no rotating shafts, displacements of the boundary, electrical effects, or any other work mechanisms associated with the control volume being considered. The kinetic and potential energies of the matter entering and exiting the control volume are neglected when they are small relative to other energy transfers. The work term, it drops out less than the heat transfer one. And it's generally you only drop it on objects that make sense. Like, for example, on the nozzle. A nozzle doesn't make work, right? So we get rid of it there. But on things that do involve some input work or output, it always stays. But heat transfer might go, right? So you just have to know what you're working with. It says in practice, the properties of control volumes considered to be at steady state do vary with time. The steady state assumption would still apply, however, when properties fluctuate only slightly about their averages, as for pressure in figure. So essentially they're showing this figure right here. So I actually got to see this. Unfortunately, I don't know if you guys will be able to do it due to COVID, but in Thermo 2, he takes you to a power plant, and I don't think I did whenever I did Thermo 2. I'm pretty sure I didn't. But he takes you to a power plant, the one over in Lake of Egypt, and you could see all these things. Like, you could see mass flow rates and pressures and all this on the screen. Like, you could see how much was coming through certain sections of the power plant, and it did vary. Like, you would see things like, fluctuations like this, But what it's saying is that the steady state can be still true, because right here are very small fluctuations, right? And this is very large fluctuations, but as long as they fluctuate equally up and down, the average stays the same, right? So essentially what it's saying is that they do fluctuate, but as long as this average value doesn't change very much with time, that steady state can be assumed, right? All right. So then we move on here. So it says, steady state also might be assumed in cases where periodic time variations are observed. Okay, so that was the second one. For example, in reciprocating engines and compressors, the entering and exiting flows pulsate as valves open and close. That is also true. Go ahead. Will you have any non-steady state problems in this course? No. Fairly certain, no. Let's put it this way: there will never be a time where, if you have one inlet and one outlet, where your mass flow rates will not be the same. But obviously, if there are two inlets and one outlet, your mass flow rate of 1 and 2 has to be equal to 3, and so your mass flow rate of 1 does not equal 3. You see what I'm saying? Essentially, if it's one inlet, one outlet, they will be the same in this course and the next course as well. So it should be easier for you. All right, and it says, however, the steady state assumption can only apply to control volumes enclosing these devices if the following are satisfied for each successive period of operation. There is no net change in total energy and the total mass within the control volume. The time average mass flow rates, heat transfer rates, work rates, and properties of the substances crossing the control volume surface are all remain constant. So basically, steady state applies when all things don't change with time, or they don't vary much with time, right? Because once again, we can talk about being negligible, right? If something, barely fluctuates with time and then goes back down and a little bit back up, we can assume that its time average value is going to remain pretty constant. And generally they will. So right here it says, next we present brief discussions and examples illustrating the analysis of several devices of interest in engineering, including nozzles, diffusers, turbines, compressors, pumps, heat exchangers, and throttling devices. The discussions highlight some common applications of each device and modeling typically used in thermodynamic analysis. So these are all in your homework, so do pay attention. I think you have an example of every single one of these, except for maybe a pump, although I'm not sure about that one. Actually, no, you should have a pump because your last question pumps it up to a higher pressure. It's up a mountain. So 4.6, nozzles and diffusers. So a nozzle is a flow passage of varying cross-sectional area in which the velocity of a gas or liquid increases in the direction of flow. In a diffuser, the gas or liquid decelerates in the direction of flow. Figure 7 shows a nozzle. So my picture, yesterday, looked a lot like this, except this one's actually good. And then this is a diffuser, right? So essentially, air go in, and because it kind of constricts the area leaving, it shoots it all through, right? You know, it shoots it through this hole over here and makes it a lot faster, right? And then the second one is the exact opposite. Smaller air intake, larger air leaving. So it says, figure 7 shows a nozzle in which the cross-sectional area decreases in the direction of flow and a diffuser in which the walls of the flow passage diverge. Observe that the velocity increases. As velocity increases, pressure decreases, and conversely for these two. So these two things. So this is something that you can know, right? If you know that if you're working with a nozzle, right, and you have a velocity 1, you know velocity 2 has to be higher. If you were given a pressure 1 and it says to find the next pressure, the one afterward, you have to know that pressure 2 is less than that, right? So these are some things that you can use as a mental check and go, ha, I found pressure 2, but wait a minute, it's higher than pressure 1 for a nozzle. That means it's wrong, right? Just some little checks and balances for yourself. So it says, for many readers, that the most familiar application of a nozzle is with the use of a garden hose. So I did bring this up the other day, but nozzles and diffusers have several important engineering applications. In figure 4.8, a nozzle and diffuser are combined in a wind tunnel test facility. Ducts with converging and diverging passage are commonly used in distributing cool and warm air in building air conditioning systems. Nozzles and diffusers are also a key component in turbojet engines. So that is one that you will do in your next class, Thermo 2. You analyze airplane cycles, essentially. And this one right here, turbojet, is the very first one you'll do. All right, so then we have nozzle and diffuser modeling considerations. So I'm not going to spend too much time on this one because we worked on this yesterday. So as you can see, this can go away, right, if we recall, because the work is negligible or nothing for a nozzle because there's no spinning shaft or anything. Potential energy also goes away simply because we're not changing height, right, from one inlet to the outlet, or we're not changing very much height, right? So then it doesn't matter. And so the main things that are left are the heat transfer and this right here. But this one, once again, as we talked about yesterday, tends to go to 0 because it's either insulated or it's because it's super small that we don't really care about it, right? So, and that's what it says right here. It says that heat transfer is unavoidable, right? Even though it says in the book it's well insulated, quote unquote, there's always heat transfer leaving, no matter how well you do it. So, but if we can limit that to such a small number, then all that's left is right here. And if you guys remember this yesterday, this is what we were left with at the end, except that we solved for H2 right here and then use this. So everybody, not yesterday, on Wednesday. I'm sure you guys remember this. And for a diffuser, it's the same thing, right? Except that some of these values switch, right, to keep things positive. So, like I said, V1 would then be larger than V2 for a diffuser. So you just have to know what you're working on. And then right here it says, so this is the application to a steam nozzle. So that's what we did yesterday. Or on Wednesday, we did a steam nozzle. We didn't usually you see air when it comes to nozzles. So at least that's what I always see in this class, and the next one is air. But this right here is a steam nozzle. So it says the modeling introduced in section 4.61 is illustrating the next example involving a steam nozzle. Particularly, note the use of unit conversion factors in this application. So this right here was this picture that they mentioned earlier. This right here was the wind tunnel, right? So they put the car here, the really nice looking one, and right, it's they nozzled it essentially. Big opening, smaller, and then out. This is the diffuser section. So right here, this is a steam nozzle. We're not going to do this question because we already did a steam nozzle, or we did a steam nozzle in on this last Wednesday. So I'm pretty confident that we can do this. So we're going to move on to another one. But they did basically the same process as us. They gave us a pressure and temperature and a velocity. And then obviously they gave us an outlet pressure and an outlet velocity, and then said find the temperature, I'm guessing. Determine the area, the exit area of the nozzle. So essentially what they did in this question, it was similar to our question, except that you needed this. So we needed to find specific volume. We have velocity too, and we know this, so you could find area. So that was the only difference between the questions. They just asked something different at the end. But it's the same exact process. I guess I should actually bring this up. So for SI units, you know how the English units were such a pain last time for doing this equation right here? The SI units are a lot easier. All you do is you make the bottom here. So you know how it's like the velocity squared minus the other velocity squared divided by 2? You just multiply this by 1,000. So it's essentially divided by 2,000. And that gets your units to work out at the end. As you can see here, you end up with times 10 to the third at the bottom. If you want to actually see it, this is what it looks like. So meter squared, second squared, and then you start canceling these things with 1 Newton is equal to 1 kilogram times meter per second squared. You get rid of the second squared, you get rid of 1 meter. And then 1 kilojoule is equal to 10 to the third newtons per meter. That goes the other meter, and you are left with kilojoules per kilogram. So, but in short, the bottom part is just 2,000. All right, let's move on. So now we have turbines. So a turbine is a device in which power is developed as a result of a gas or liquid passing through a set of blades attached to a shaft free to rotate. So this is how essentially all of your power in any application is made for like cities. This is exactly how it's made. I'm pretty sure in most, I can't imagine any ones that don't use a turbine, except for like photoelectric, but that, or photovoltaic. I can't remember which one it is, which one's the one that, it's for solar cells essentially. That one doesn't have a turbine blade, but that one's not large scale yet. Is it voltaic? Okay. So it says a schematic of an actual flow steam or gas turbine is shown in 4.9. So this right here. Such turbines are widely used for power generation in vapor power plants, gas turbine power plants, and aircraft engines. So we will see this in there as well. In these applications, superheated steam or gas enters the turbine and expands to a lower pressure as power is generated. A hydraulic turbine coupled to a generator installed in a dam is shown in Figure 10. So essentially this one uses potential energy and kinetic energy instead of something else. So for example, what it does is essentially, and I think there is one of these in Missouri. It's like, I can't remember what it's called, but I actually went to a presentation on the guy who ran the power plant. It was brilliant. Because while he was there, he got hired. This is going to be a fun story, but he got hired on to be the full runner of the power plant, and then 4 months later, the whole dam caved in. Water spilled into the national park. It killed somebody. It was like a huge problem that they thought they were going to have to shut down the dam forever. They were like, yeah, that was not good. And I wonder what it's called. I'll have to look it up so you guys can look into it. It was a very interesting story. And he actually managed to keep his job, which is good. But yeah, it was remarkable, and it still works today. And it's a hydroelectric plant. Essentially, what happens is that water is up like a big hill at a higher elevation, and they release it down into a turbine. And as it runs down the hill, essentially it picks up velocity, and it essentially just smashes into the turbine blades and spins them. And then they pump that water right back up to the dam, and so it just keeps going like that. And pumps don't actually, they're not really expensive when it comes to power usage, so you end up getting more in or more out than you had to put in. So that's hydroelectric. So it says, today hydropower is the leading renewable means by producing electricity and is one of the least expensive ways to do so. Electricity can also be produced from flowing water by using turbines to tap into currents in oceans, rivers. So this one's actually something they do in a couple of nations, like in the north. They have turbines that essentially sit in the water, and as waves come in, they spin the blades, and they send the power elsewhere. So there's a lot of different ways that they do it, but they obviously the waves one is kind of like not as big, but this stuff's really interesting. Like whenever you get to Thermo 2, this stuff is amazing. I love this class. All right, so it says, and we'll just move on from there. So this right here is actually the picture of what it looks like. So yeah, this is the reservoir, and then this right here that spins it. So and that can't, I'll have to find out what the name of that plant was, but essentially what happened to them is that this right here, this dam, was made of gravel and like a bunch of like really bad materials, and so eventually water was just leaking through, and it made like a big hole, like, you know, like a big structural hollow area, and then it just all collapsed in, and all the water rushed out, and like I said, it killed somebody. The park ranger that lived in the park, killed him. His family was found in the car, like miles away from where they lived, up a tree or something. Yeah, it was a really rough. It was really bad, but it still runs today, though. All right. And then we have steam and gas turbine modeling considerations. So this right here is what you will get when you work with the steam and gas turbines. So once again, QCV, work CV, mass flow rate, H1 minus H2. So these right here tend to go away. Definitely the potential energy goes away, just simply due because potential energy, your turbine is always going to be on the same level. Like there's no reason for it to, like, it really can't be higher than than another part of the turbine. So this part definitely goes away. There are some times where it says that they will give you an inlet velocity on a turbine. So if they give you a velocity in the question, then you know it has to stay. But for generally speaking, these things go away. And you are left with the following. You are left with heat transfer minus work plus mass flow rate times H1 minus H2 is equal to 0. So this is what you will be left with when working with gas turbines. And steam turbine is the exact same thing, more or less. But remember, sometimes, and actually a lot of times, they will say that, assume heat transfer is negligible, or they will also say that the heavily insulated turbine, then you will get rid of this, and you'll be left with this equation right here, which is just the work of the turbine is equal to the difference in enthalpy at states at before and after. This equation right here is super valuable, and it'll be used in this class and Thermo 2 definitely. You will use this a lot, so I would hold on to this in your memory bank. All right, so then we have application to the steam turbine. In this section, modeling considerations for turbines are illustrated by application to a case involving the practically important steam turbine. Objectives in this example include assessing the significance of the heat transfer and kinetic energy terms of the energy balance and illustrating the appropriate use of energy conversions. So we will probably do this question, but I still have time, so I'm going to move on. So we'll hold on to this one. So then we have compressors and pumps. So compressors are actually just basically inverse turbines. like more or less. But pumps are a little bit different. So we will talk about both of them. So compressors and pumps are devices in which work is done on the substance flowing through in order for them to change the state of the substance, typically to increase pressure and or elevation. The term compressor is used when the substance is a gas. So remember that. Compressors, just like you would pump into your like car tires, you know, like or like you would compress air and put it in there and pump your tires pressure up. Compressors are used for gas. Pumps are used for water or a liquid, right? All right, so it says 4 compressor types are shown in Figure 11. The reciprocating compressor, Figure 11A, features reciprocating motion while others have rotating motion. It says the axial flow of compressor 411B is a key component of turbojet engines, also true. Compressors are an essential components of refrigeration and heat pump systems, also true. Vapor, that would be in Chapter 10, which is refrigeration, in the next class, not in this one. In the study of Chapter 8, we find that pumps are important in vapor power systems. Big true. Pumps are also commonly used to fill water towers, remove water from flooded basements, and numerous other domestic and industrial applications. I actually just did this the other day. I had to use a sump pump to shoot all the water out of the hot tub. So I used a sump pump to get it out. So I just did this. That's a real life application there, guys. So then we have compressor. So these are all the ones they were talking about here. So this right here is the reciprocating one. So essentially as this thing spins, it's pumping it in, drawing it in, right? So this is a valve right here. So it shoots down. It kind of reminds me a lot of a car engine, right? Essentially like as this thing retreats or comes closer, it pulls in or it shoots more out and it presses it. So whenever this thing draws back up, it pulls all this in and then it presses it into a smaller area right here, and then this valve opens up. And then over here we have axial flow. So this is the compressor that we are going to see the most in our classes. So whenever I say compressor, this is what it's going to look like. So then we have centrifugal. So this one is a turning one, and then this one right here. Wow, I haven't seen this one. Okay, I'll have to look at a little more at that one. I've never seen that one before. But we have the following. So then we have here 4.81 compressor and pump modeling. So once again, we have to figure out what each one of these things do. So pretty straightforward for compressors and pumps. We get rid of a couple of things. So obviously a compressor or a pump, we are going to use power, right? We are putting in power because you don't just increase the pressure of something by and it makes work for you. It doesn't, because it's not an expansion process, it's a pressure process, gaining process. We have work, which is a negative work. We have to put this in. Heat transfer, like the turbine, is generally reduced to 0 because we just say it's well insulated or it's just small relative to everything else. So then we have here heat transfer with the is neglected, and then we have the following, which is the work. The control volume is equal to M1H1 or MH1 minus H2. So it's the exact same thing as the turbine, except when you do this, you will get a negative number because H1 will be less than H2. Because H1, because remember, enthalpy for steam is based on temperature and pressure. And if we get a higher pressure here, temperature goes with it, so therefore H2 will be higher, and so you will get a negative number. And the reason why is because the work going in has to be negative, right? Because it is a compressor. And it says for pumps, heat transfer is generally a secondary effect, but the kinetic and potential energy terms may be significant depending on the application. Be sure to note that for compressors and pumps, the value of work CV is negative because a power input is required. I just said that. All right, and then we have applications to an air compressor and pump system. So right here, this is an air compressor. Like I said, this is exactly how you will see it mostly. And I think in your homework, you either have a compressor. I think you have an air compressor. Let me see if there's anything else here that I need to get to. Oh, wow, look at this. I hope you guys have the book because this question looks a lot like your last question. So that would be super helpful. Let me see if there's anything else I need to get through. I don't know if I want to do this one yet. It says, no, we're not going to do this one yet. So what we're going to do is we're going to do a question right now. So for the last 15 minutes, I'm going to go up and I'm going to do a question. Which one would you guys want? You guys want a compressor? You are not, this one is not allowed because it's basically your last homework question. So we're going to move something here. We should probably just do the turbine then, yeah. Let's do the turbine. So, turbine. So this is the power generating process for most power cycles, or basically all of them almost. So I'm going to go ahead and do what we always do here, guys. We're going to start the question with what we know and what we can use, all right? So let's go ahead and grab a text tool and turn down the old text. All right, so let's go ahead and do this. So knowns. Step one is always write this down. So it says steam enters a turbine. So obviously we know that it is steam, right? Which is water vapor. Operating at steady state with a mass flow rate of 4,600 kilograms per hour. So a steady state, so that means M1 is equal to M2, right? And we also know that M1 is equal, well, I'll just go ahead and write that on the same line, not to be annoying, is 4,600 kilograms per hour. Now, you guys would be smart to turn this into seconds, a kilograms per second now. And the reason is because it asks which, we'll get to that in a minute, actually. Never mind. We're going to stay straight in line here. It says the turbine develops a power output of 1,000 kilowatts. So we have work is equal to 1,000 kilowatts. It says at the inlet, so now we start getting into states, right? So state 1, I'll just do this. So pressure 1, at the inlet the pressure is 60 bar. And the temperature is 400 degrees C, so T1 is 400 C. All right, now we can move over here, and it says, and the velocity is 10 meters per second. So they have given a velocity, which means that we cannot neglect it. And then over here it says at the exit the pressure is 0.1 bar. So pressure 1 or pressure 2 is equal to 0.1 bar. And then it also says, and the quality is 0.9%. So x2 is equal to 0.9. So they have given us a quality. Come on. X2 is 0.9. It says the velocity at the exit is 30 meters per second. So we have velocity 2. So V2 is equal to 30 meters per second. So as you guys can see in this turbine question, this difference in velocity is not in much at all. But since they gave it to us, we're going to use it. So, and it says, calculate the rate of heat transfer between the turbine and the surroundings. So our goal is to find the heat transfer. So Q from 1 to 2 is that. So that is what we know. Now let's move into some things that we can do, right? So the first thing I would suggest doing is, once again, writing out the equation. So let's write out the equation for this. So a turbine at steady state is equal to the following. So it is Q minus W plus M times H1 minus H2 plus V1 squared minus V2 squared. And this is all over 2. So this is the equation that we're working with, right? So I'm going to go ahead and maximize this. So that is the equation that we're working with. So I'm going to write this. Let's go ahead and do this. So turbine at steady state. There. So now we need to do some looking up of properties, right? So our first step is that we should start finding these things, since we have basically none of these except for work, right? And the velocities. So we need to find H1, H2, and Q is obviously what we're trying to find. So we need H1 and H2. So let's go with that. Let's start with state 1 over here. So I'll just find a spot. State 1. So state 1, they have given us a temperature and a pressure. So our goal here should be to go to the tables, which I'm going to now. And remember, this is steam, and we're using SI units. So we need to just go to the very first table for steam, which is this one right here. But like I said, because was given a pressure and a temperature, I always like to go to the pressure table. And it said that it was 60 bar, if I recall. I'll go back and look to be sure. 60 bar. So 60 bar, you go across here. So we are at table A3. You go across from 60 bar, and you'll read that the temperature here is 275.6. Our temperature was 400, I'm fairly certain it was, which means that we are what? We are superheated, right? We are way higher than the saturated temperature, which means we have passed it, which means that we are a superheated vapor. So now we must go. And really quickly, if you are going into a turbine, this is just a check for you guys. It should basically, it'll always be superheated vapor, unless it's a Carnot turbine cycle, which we'll get into that one way later. But just know that if it is a turbine question, and it is going into a turbine and it has one inlet, one exit, it is a superheated vapor going in basically every time, 99% of times, because that's how you're gonna get the most power out of it. So it doesn't make sense to do it any other way. So right here we have 60 bar in the superheated tables. Now we must go down to 400, so we must cross over. Here, we now have H, U, V, whatever we want. But we are going to take H here, because H is the one that we need, right? So 3177.2. So I'm going to go ahead and take that. So table A4. We have H1 is equal to 3177.4. Is that what I said? 0.2. Okay. 3177.2 kilojoules per kilogram, right? And you can grab everything else, but because I think I know that the question we don't need to, I'm not going to. But honestly, you can write it down. And it's never going to hurt you, right? If you take V1 here, it'll never hurt you to do it. So 0.04739. Holy crap. 0.04739. And this is kilojoules per kilogram Kelvin. So we've got state 1 all figured out, right? Pretty straightforward. Now we must go to state 2, right? So we have found H1, we have M, we have V1, we have V2, and we have work. So only one thing missing from now. So let's move down to state 2. So state 2, we were given pressure 2 is 0.1 bar, and we were given X2 is 0.9. So that should have been red flags in your head. As soon as you saw that they gave us an X2, it means this is saturated. We are now saturated. We are under the umbrella curve in the middle, right? Under the saturation curve. So that means we need to go to the saturated tables and go to 0.1 bar and start picking apart some values here. So let's go ahead and do that really fast. So let's go back up to the saturated tables. We have a little ways to go. Right here. So 0.1 bar is right here. And if we go across here, we have to start grabbing things. And so we were given a quality, which means that we don't have to find one, right? We were given one, we know what it is, which means that we need to now find our H2 value. And our H2 value, because it is inside of this table, means that it is somewhere between Hg and Hf. And because it's 90%, it means it's closer to Hg than it is Hf by a lot. But we still have to find the actual number for it. So we're going to do that. So I'm going to move this table over here, because I need to be able to see a little bit. I'll zoom it back in a minute. Okay, so right here, if we go up to 0.1 and slide over, we need to find H2. So H2 is then equal to the equation, you remember from previous sections, it's HF plus X2 times Hg minus Hf. Or if you want to just use the value HFG, it is also here listed, and I will do that. So H2 is then equal to our HF value at 0.1, which is 191.83. And this is all kilojoules per kilogram, by the way. 191.83 plus our X2, which is 0.9, times our Hg minus Hf value. And like I said, Hg minus Hf is already in the table here. It is Hfg, which is 2392.8. So it is this middle column between the two. And this is only, I think, in SI units. I don't know if they do it for English. I might be wrong, though. But they have this in, just know that HFG is that. It's just the difference between these two. So if you use this one and subtract off this one in your calculation, you'll get the same thing. And so, now I have to pull up the old calculator. So we have 0.9 times 2392.8 plus 191.83. 45.35. So that is what we have got just by using that simple saturated equation, using quality. This is our answer. And it makes sense, right? Because the maximum value is 2584. And so we're fairly close to that, right? Which makes sense to us, right? If it was way down here, then obviously we've messed up somewhere. But this is right. So now that we have this, we now have everything we need to solve this equation, right? We now have Q can be solved in terms of all the other things. So we are going to do that. So I'm going to go ahead and get rid of this out of my face and move over a little bit. So I'm going to start with the text box over here, and this is going to be a solution. So now what we have to do is we have to solve and get Q by itself. So there's a couple ways you can do this. You can move everything to the other side. Like I said, that's, you know, whatever you want to do. I'm going to move everything to the other side. So we're going to do Q is then equal to, right, work. And it's going to be plus M H2 minus H1, because essentially I had to flip everything's sign because we moved it. We essentially moved it, right? So we subtracted it, and I just moved the negative through. So everything is going to flip directions. Plus V2 squared minus V1 squared over 2. And if what I did there was like not, you don't understand it, let me know. But essentially, over here in this equation, I've added W to the other side, so that's how we get the W here. And I've subtracted this whole quantity off. And once I've subtracted it, you can just move the negative through, and you can add the opposite, which is H2 minus H1, and then plus V2 minus V1 squared. So this is what we are left with, is the following. Now we can fill it in with our numbers. So we have Q is then equal to 1,000 kilowatts plus our mass flow rate of 4,500 kilograms per hour. I thought it was 4,600. Oh, it is 4,600. I just wrote it wrong. Here. So it's 4,600. Sorry about that. So now There's a problem though, and I'm pretty sure some of you probably have already seen it, and I mentioned it slightly earlier, is that we have 4,600 kilograms per hour here. And why this won't work is because we have kilowatts here, which is a kilojoule per second, right? So we need this in terms of seconds. So what we have to do is we have to divide by 3,600, right? Because 60 minutes in an hour, 60 seconds in a minute, 3,600. So we need to divide this by 3,600, in my opinion. So I will do that right here on the screen. So 4,600, or is it times? No, it's not. It's the other way. Sorry. I just freaked out for a second, of course. So it is divided by 3,600. So 1.277. 1.277 is our mass flow rate per second. So 1.277 kilograms per second is how I've just changed it. And then we multiply by this over here, which is our H2 value, which is 2345.35 minus 3177.2 plus, although I'll make that a quantity, I'll get that by itself so it doesn't look weird, plus 30 squared, right, because it was V2 is 30 squared, minus 10 squared over 2. So, but also, like I said, to turn this into kilojoules per kilogram, we just multiply by, so divide by another 1,000. So essentially it's 2,000 down here. And that was in that units thing I showed you earlier. So if this is our equation, we can now work on it, right? Although I really am gonna have problems doing this on this. Every week I say I'm gonna get my calculator out, but I never do. So real fast, I'll just go back here then, because they actually probably solve it. So we'll go through and see if we got it right. So this is the equation they wrote first. Then it broke down to this. So like I said, so they did the way that I did. It's QCV is equal to work CV plus, and they flipped all the quantities around because it was add the opposite. Then they found H2 to be 2345.4. Our value was 2345.35, so they just rounded up. Then they did the quantity H2 minus H1 is negative 838 or 831.8, right? And then they did V2 minus V1, or V2 squared minus V1 squared over 2 is 0.4 kilojoules per kilogram. So right here, guys, you can see that the velocity, the kinetic energy, tends to not be very significant, right? It tends to be very, very small. So although because these were very small velocities, it's very small, but even if this was huge, you know, we're talking like if there's a big difference, you'll get a very small number too. You'll get like 5 or something. It won't be very much ever, but it's still significant if there's a big enough velocity difference. And so they have these two quantities, H2 minus H1 here, and you have V2 squared minus V1 squared over 2 is here. And so then they put this all together. So we have 1,000 plus 4,600 divided by 3,600. So I'll just do this on the screen as well. So they have 1,000 plus 1.277, I think is what we got. I'll make sure that 1.277. That's not going to work. We're just going to do it the old-fashioned way. 1.2778 times negative 831.8 plus 0.4 is that. And so the difference between this is, then you add 1,000 to it, and you get the following. You get 62.36292, and this is kilowatts. So that makes sense though, guys, right? So really fast, we have gotten a heat transfer of 62.3 kilowatts. Why does this make sense? The reason why this makes sense is that heat transfer is not coming into this, right? It is leaving. And the reason why you can figure that out is because we are coming in at, essentially there's really high temperature in here, right? There's 400 degrees here, right? 400 degrees coming in, and it leaves at, let's go look at that temperature. It leaves at 45.81, right? So essentially inside of this whole process, you have very high temperature coming in, a little bit lower, but it's still high, right? Like 45.81 degrees Celsius is high. That's way above. That's double room temperature, essentially. So for heat transfer to go the other way, this room would have to be massively hot. And so that's why heat transfer is going out, right? It is leaving the turbine to the room because the room is colder. So it makes sense that we have a negative heat transfer. Heat transfer is not coming in. It is obviously leaving. So this right here, this solution makes sense to me, and it's the one that we got as well. So all good on that front. I'm going to go ahead and take attendance. If there are any questions, you guys feel free to ask. But this is another question that you'll have to do in your homework, so hopefully it made some sense.